Hello everyone and welcome back to Math Made Easy. In our previous lecture, we introduced numerical integration and studied the trapezoidal rule. The trapezoidal rule approximates a curve using a straight line. But what if we want a better approximation? Or instead of approximating the curve using a linear polynomial, we can approximate it using the quadratic polynomial. And this gives us the Simpson's one-third rule. So today we will understand the basic idea and derive the formula, learn the important conditions and solve the numerical examples using both the single application and composite the composite Simpson's 1/3 rule. So suppose we want to estimate the value of I as this integration from a to b fx dx. So in the trapezoidal rule, we approximate fx by a straight line. But in Simpson's one-third rule, we take three equally spaced points, as is x0, x1, and x2, and fit a quadratic polynomial through them. So instead of a straight line approximation, we use a parabola. And the area under this parabola gives us an approximation to the integral. So the key idea becomes if there will be a three equally spaced points, then you need to use the quadratic interpolation and hence you need to integrate it. Now there are some conditions for Simpson's one-third rule, which is extremely important for the examination point of view. For the basic Simpson's one-third rule, we need two subintervals. That means we need three equally subspaced points. That means we need three equally spaced points. So if the interval is divided into n equal subintervals, then for the composite Simpson's one-third rule, n must be even. For example, we can take this n as 2, 4, 6, 8 and up to so on are valid. But if n equals to 3, 5, 7 and so on, that can't be used directly with the composite Simpson's one-third rule. So that means the Simpson's one-third rule is basically having the even number of subintervals. Now let's just derive the formula. Just need to take the three equally spaced points as is x0, x1 as x0 plus h and then x0 plus twice of h. Now using the quadratic interpolation polynomial, we can write the function approximately as is fx as p2x. So after integrating this quadratic interpolation polynomial over the interval from x0 to x2, we obtain this integral as from x0 to x2 fx dx as h by 3 times f of x0 plus 4 times fx1 plus fx2 approximately. And this is the Simpson's one-third rule. Now notice the coefficient as this 1, 4, 1. So this pattern is extremely important. Whenever you see a Simpson's one-third rule, remember there will be this 1, 4, 1 with the factor h by 3. Now let's just write the formula clearly. For two subintervals, we can take this I as h by 3 times f0 plus 4 times f1 plus f2, where this f0 as f of x0, f1 is f of x1, f2 as f x2. So remember this x1 is having, so this x1 becomes this x0 plus h and this x2 becomes x2 plus twice of h. So the 3 points must be equally spaced. Now we have a quick question here where we need to evaluate approximately this integral 0 to 2 power x dx using the Simpson's one-third rule. So we have this a is equals to 0 and b equals to 2. So for Simpson's one-third rule, we use the two subinterval. That means n equals to 2. So just calculating the value of h as b minus a by n. That means it's 2 minus 0 divided by 2. And that gives you 1. So our points become this x0 as 0, x1 as 1 and x2 as 2. Now calculating the function values as this f0 as 1, f1 as e which is 2.7183 approximately and f2 as 7.3891 approximately. Now using this I approximately equals to h by 3 times f0 plus 4 times f1 plus f2 and then substituting the values, and that gives you this 1 by 3 times 1 plus 4 times 2.7183 plus 7.3891, and hence we got this as 1 by 3 times 1 plus 10.8732 plus 7.3891, and that gives you 19.2623, which becomes approximately 6.4208. So the Simpson's one-third approximation is approximately 6.4208. Now suppose we have more than two subintervals, then what? For example, we have Sn equals to 4, and we can divide the entire interval into 4 equal parts and apply the Simpson's one-third rule over the pair of subinterval. And that gives you this composite Simpson's one-third rule. And the formula becomes this h by 3 times f0 plus 4 times f1 plus 2 times f2 plus 4 times f3 plus 2 times f4. So for a general n, we have this I is approximately h by 3 times f0 plus fn plus 4 times f1 plus f3 and up to fn minus 1 plus twice of f2 plus f4 plus up to fn minus 2. Now look carefully at the coefficients. They follow a particular pattern, that is this 1, 4, 2, 4, 2, 4 and up to 2, 4 and 1. So this pattern is actually the key to using the composite formula correctly. Now let's just discuss the accuracy. The composite Simpson's one-third rule having a truncation error of basically of order h power 4. And basically this is higher than the composite trapezoidal rule whose error is order of h square. Therefore, for sufficiently smooth functions and comparable step sizes, Simpson's one-third rule generally provides a more accurate approximation. Now let's just compare them. We have the trapezoidal rule, which approximates the function using a straight line, or is having the order of h square as accuracy. Whereas we have the Simpson's one-third rule, which approximates the function using a quadratic polynomial and is having order of h power 4 accuracy. So the Simpson's one-third rule generally gives you a better approximation when its conditions are fully satisfied. So let's just quickly summarize the today's lecture. And the Simpson's one-third rule uses a quadratic approximation. For two subintervals, we can take this I as h by 3 times f0 plus 4 times f1 plus f2. For an even number of subintervals, we can take this as I as h by 3 times f0 plus 4 times f1 plus 2 times f2 plus 4 times f3 and so on. So the most important condition becomes this n should be even. And finally, this error becomes this order of h power 4. And for the standard composite Simpson's one-third rule. And that's the end of today's lecture on Simpson's one-third rule. We learned how Simpson's one-third rule uses a quadratic approximation, derived its basic formula, studied the composite version and solved the numerical example, and hence discussed its accuracy and important conditions. And the three things you should remember is this h by 3 and the pattern in the coefficients, and this n should be even. So in the next lecture, we will study the new Simpson's 3 by 8 rule, another important Newton codes formula. So if this lecture helped you, please like the video, share it with your classmates, and subscribe to Math Made Easy. Until next time, keep learning, keep questioning, and keep practicing, and I'll see you in the next lecture.